Hello friends. Today we will discuss with the topic the antigen antibody interaction. We can see that an antigen may be if may be having different epitope on its surface. At the same time, an antibody monomer can bind with, if this is the antibody, it can bind with two antigen binding site 1 and 2. And I have drawn it with green, which shows the specificity. Just imagine this is the specific to this one. That means this can bind with this one. This can bind with this one. And we can see that if this is the specificity, I can say that antigen is multivalent with multiple determinants or the epitope. So this is known as the epitope. And so we can call it is having multi determinants, and whereas this is known as the paratope. So we can see that an antigen binds with the antibody between the epitope and the paratope. Epitope is the antigenic determinant, whereas the paratope is the antibody determinant. So an antigen is multivalent or multi-determinant. So what we can see is that when an antigen is present, it can bind to an antibody. It can bind to, in fact, many antibodies of with different specificity. Like for example, it can also bind with an antibody having this specificity. It can also bind with another antibody which is having this specificity because the epitopes on it are different. And at the same time, a single antibody can bind with, it can also bind here. So a single antibody at a time can bind with two different antigen. Likewise, what we could see is that if there is many antigen, many antibody, they club with each other, forming a lattice like structure, or they form a meshwork like structure. And if I could speak it by explaining it as a graph, and I'm taking the x-axis as antibody concentration, and I know that if in a system I'm having lots of antibody, if I'm going to add antigen from outside, what I could see is that, and if I can divide this graph into three, that is in this region totally I could see that the amount of antibody is high. As and when antigen is added, the lattice will be formed, and the lattice gradually goes on increasing. And so as amount of antibody, as and when antigen is added, they bind with the antibody and forms lattice or the meshwork. And it reaches a peak when I could see that the amount of antibody is equal to the amount of antigen added. Now, even if further if I add antigen, I could see that the amount of antibody is being coming to the maximum. So the maximum lattice formation will be here. After which, if again I am adding antigen, I could see that since all the antibody present in the system is being bounded with antigen, and no antibody is present more to be bound with antigen, the lattice formation goes on down. And we can see that I can name the three zone as here. If I see here, the antibody is excess, and here maximum antigen antibody complex. And here I can see that antibody are all used up, and here it is antigen excess. So I can see that the amount of complex formed in antibody excess and antigen excess region will be least and the maximum will be seen in the here, where both the antigen antibody are of equivalent zone. Here it is antigen antibody equivalent zone. So here I can call it a zone of equivalence. Now coming back to the forces what bind this antigen and antibody, I can say that there are many intermolecular forces which are being responsible to bind an antigen with the antibody. These are electrostatic forces, hydrogen bonds, hydrophobic bonds, and van der Waals forces. And now we'll be discussing about the antigen antibody interaction. So here the properties or the features of these interactions, we start with the specificity. That is very clear to us that an antigen antibody interaction is uh, is very much specific, and a single type of epitope can bind with only a single type of, specifically with a single type of paratope. And next one is the antibody affinity. Antibody, the second feature is antibody affinity, and the antibody affinity is the strength of the reaction between a single epitope and a single paratope. And since the binding bit antigen and antibody is by a known covalent bonds, we have seen, right, like hydrostatic force, hydrogen bonds, hydrophobic bonds. So since it is the bonding between an antigen and antibody is by a known covalent bond, so it will be very this bonding will only happen if the molecules are very closely packed. So the distance, so the binding strength always depends upon the distance, at the same time compatibility, that is specificity of two substances. So affinity speaks about the strength of the reaction between an antigen and antibody. Next is avidity, affinity, antibody avidity. Antibody molecules and antigens, we are very familiar that they are multivalent. And this multivalency of an antibody at the same time antigen, they tend to increase the chance of interaction. That means there is always a high probability of binding with a antigen to an antibody, and also the strength of bonding will also increase since they are having multivalency. They don't need to wait for a single antigen or a antibody. So binding of antibody to an antigen at more than one side, they increases the strength of bond, or we call that complete strength, we call it as the avidity. And avidity is influenced both by the valency of both the antigen and antibody. More they are having multivalency, more will be the strength of their binding. So it speaks about the overall strength of the bond formed between the antigen and antibody. Next is cross reactivity. Cross reactivity is also a property contributed by the multivalency of an antigen and antibody. We can see that a single antigen can bind, since it is having multiple determinants or epitope, at the same time this can bind with more than one antibody. So that speaks about a cross reactivity, that is a single antigen binding to more than one antibody, and a single antibody at the same time can bind with more than one antigen. So that speaks about cross reactivity. Next is antigen precipitation. That speaks about when an antigen is a it is soluble, an antibody binds with the soluble antigen and it forms a insoluble complex. The antigen antibody complex formed is insoluble. Now I can call that insoluble complex as precipitation, and the antibody which is responsible here in this reaction can be named as precipitin. Next is bonus effect. The bonus effect is also another contribution of a multivalency property of antigen and antibody. That means if a single antibody holds two antigens simultaneously, the strength of the bond is very weak. That means, but then we can see that here it is not a single antigen or a single antibody coming into an action. We can see that at the same time the antigen will be bound by another antibody also. So but if an antigen, so here we can see that if an antigen is bridged between two or more antibody, the strength of binding will be increased, and that increase of strength I can call it as bonus effect. That is, together we stand, what we say, together we stand, together we stand, and divided we fall, the same way. If single antibody is only is present, the bond formed between the binding will be very feeble, it will be weak. But at the same time, the same antigen is bounded by more than one antibody at the same time. So we can see that since there is binding with more than one antibody, the strength of binding will be increased. Now we will speak about the functions of antibody. Functions, when I say about the functions of antibody, I can say that antibody is having different functions to play. First of all, we know that the main role is that antibody can bind with the antigen. But then that binding, that processing is in different way. So we'll start with the first method, that is agglutination, which may be familiar for you. You might have heard about the blood agglutination. Blood, when two different blood groups are clubbed, it forms a kind of precipitation. But then this is not a precipitation actually. We call that clumping formed as agglutination. It is because in agglutination, the antigen will be a insoluble antigen. So likewise, if I speak about the blood, that antigen is seen on the surface of the blood cell, RBC. So it is insoluble. So we can see that that antigen, when combined with a antibody, it forms an antigen antibody complex, and that causes a clumping, and that clumping I call it as agglutination. And that agglutination, the antibody which is responsible for agglutination, I can call it as the name agglutin. And here also the multivalency is the factor which contribute this kind of clumping, because a single antigen with many epitope will bind with more than one antibody at the same time, and the antibodies at the same time can bind with two different or two or more than two antigens at the same time if it is a pentavalent or a dimer at the same time. Next, we can speak about the second function, that is precipitation reaction. Precipitation reaction is the same, it works in the same way as agglutination, but the difference is that in precipitation reaction, the antigen will be soluble. So when a soluble antigen binds with an antibody, antigen antibody complex is formed. That complex is no more soluble, it becomes an insoluble precipitation, and uh, that phenomenon I call it as precipitation, and the antibody involved I can call it as the precipitin. Next, I can say about neutralization. When I speak about neutralization, I could see that it is the property of antibody to cover all the epitope and making the antigen no more uh, exposed to the outside. It is the epitope which gives them the power of causing problems. So what the antibody do is they'll cover all the epitope, they'll block all the epitopes of an antigen, so that antigen now it is in a neutralized condition. And once a antigen antibody complex formed, it will be further destroyed within the body. And we can see that this destruction happens like when this complex is formed, they are made more prone for the phagocytosis. So next, function of antibody. So the fourth one is the opsonization and phagocytosis. So what does it mean? So we'll just come back to the black whiteboard. Here we can see that if there is a uh, like if there is an antigen like this, and if it is having an epitope, what we could see is that this antigen is made more attracted to a phagocytic cell present. If this is the phagocytic cell present, and here it is made more attracted to this phagocytic. This is made more attracted to this macrophage phagocytic cell by the attachment to a antibody. And this we can explain like this. Here we can see if this is the antigen, this is the antigen binding site of the antibody, and this is the Fc part. And here this phagocytic cells may be having a receptor which we call it as Fc receptor. So what happen is that this I'll draw like this. So what happens is that when antigen is present in the body, it will bind with antibody, forming antigen antibody complex. Once such complex is formed, that once such complex is formed, that will bind to the receptor seen on the Fc receptor seen on the macrophage. And what we can see is that this can be explained as if there is an ice cream on a bowl, ice cream, vanilla ice cream in two bowls, and in one the ice cream is being in one the ice cream is being uh, it is being garnished with chocolate chips. So here you could see that this ice cream is more attracted to a children. Just imagine the phagocytic cell is you or the children, and this blue one you can imagine chocolate chip as antibody and the vanilla ice cream as antigen. So when compared to this one, this ice cream is more attracted for a children. This is because it is same way the opsonization process function, that is the antibody is making the chocolate chip is making the antigen, the vanilla ice cream, more attractive to the children. So here the antibody is known as opsonin, and the phenomenon is known as opsonization. I'll explain. Opsonin are molecules which make the antigen more attractive to the phagocytic cells. That means it is an intermediate molecule. Here, this antibody is acting as an intermediate or opsonin, and this phenomenon of making an antigen more prone to phagocytosis, I call it as opsonization. So, this function of antibody, we can say it as the antibody mediated opsonization. And once it is being attracted to phagocytic cell, the normal reaction happen, that is phagocytosis, which we have discussed earlier. That is, they are being engulfed, phagosomes form, and the phagosomes will collide with lysosome, forming phagolysosome, and then they will be digested and they will be thrown out of the phagocytic cell. Next, we can speak about the next function. The fifth function is the antibody dependent cell mediated cytotoxicity. As a name indicates, we are speaking about the functions of antibody. We are speaking about the antibody, how they bring about the destruction of an antigen in different ways. So here we can see, here this is the microbe, And you could see that once a microbe enters, antigen enters, it is bounded by the and the antibody. So now they form antigen antibody complex, and they will go and bind with some of the killer cells, like natural killer cells. And how an antigen antibody complex bind to a natural killer cell is that the natural killer cell will also have a receptor, and that receptor I call it as Fc receptor. And we know that antibody have Fc part. So once the complex is formed, these complex go and bind with the natural killer cell on its Fc receptor with Fc part of the with the Fc part of the with the Fc part of the antibody. Like you could see, if this is a natural killer cell, if this is the Fc receptor, you could see that if there is an if this is the antibody, if already an antigen is present here with antigen determinant, and here if this is being bound by a antibody, if this is the antibody, this is the Fc part of the antibody, and here this is the antigen binding site, this is the antigen binding site, and this is the antigen, and this is natural killer cell, and this is the Fc receptor. So what I meant to say is that with the once the antigen antibody complex are formed, with the Fc part, it go and bind with the Fc receptor. Once they bind with the Fc receptor, natural killer cells may be having many kind of pharmacologically active compounds in it that will be released, and they causes some pores. They develop pores. They develop pores in the they develop pores in the they develop pores here they'll develop pores in the antigen, and the damaged cell or the cancerous cell will be destroyed. So here, when I speak about antibody dependent cell mediated cytotoxicity, it is meant when a cell is damaged, a microbe is being damaged, a microbe enters the body, it is being bounded with antibody, forming antigen antibody complex, and the complex will bind with the natural killer cell by the Fc receptors, and the antibody will be damaged. Next, we can speak about a complement activation. Before we move with that, we should know what a complement. Complements are nothing but complements are some proteins which is present in my blood, and there may be about 30 or more such complex in my blood. And normally, these proteins will be in an inactive form. They may be a proenzyme, I could say, inactive enzyme form, and they become active only when then an antigen enters the body. As the name indicate, why we have given complement terminology is that these protein will help antibody to bring about the immune reaction. That is, it helps the antibody to carry out immune reaction, a complementing system. That's why we are calling those protein as complement. So antibody, they binds with when an antigen enters, as I said, this complement molecules will be in an inactive form. They will become active when and only when an antigen enters the body. So what happens is that when an antigen enters the body, they bind with antibody. Now what form is? It is forms antigen antibody complex. Once the complex is formed, what we can see is that this complex will will activate the complement molecule. And once the complements, as I said, 30 or protein like complement proteins will be present, and how they are being activated because of the in a cascade manner. That is, once one complement molecule is active, it makes the another inactive to active form, and that will make another inactive complement to active complement molecule. Likewise, there is a cascade of reaction leading to a end reaction, that is the destruction of the antibody or a damaged cell. So we can see that this this is another function of antibody, that is to activate the complement. So what the antibody do is, antibody bind with antigen, and once antigen antibody complex is formed, they activate the complement proteins present in the blood. So that was another function. So we have discussed with fifth one. Now last one we can see is then it is complement reaction. How is the reaction happening is that what they do is, once a complement system is activated, they start releasing some kind of chemicals, and that chemicals will cause holes on the surface of the antigen, and that we call it as membrane. This membrane will be lost because of formation of transmembrane pores. So these are the different functions of antibody. So I'll just I'll just show you the pictures here. First one, as we said, it is the agglutination. You could see the picture. Here it is the rectangle one, which shows the antigen bacteria and that antibody. So a single antibody is bound with more than one antigen, and the same and one antigen is bounded by more than one antibody. So they form a clump-like structure. Next one we can see, this shows the phagocytosis. That is, the antigen is made more attractive because of this. Why? Because the phagocytic cells already have a receptor for Y, that is antibody, not for the antigen. Next, you could see here it is antibody dependent cell mediated cytotoxicity. That is the destruction of cell that remain external to the target, like they become more like, for example, if there is a parasite, and if this is the parasitic cell that is attracted by the green color antigen, and we can see there is an eosinophil, that is the effector cell, and they may be having Fc receptor. So this parasite will bind with the antibody, and they form antigen antibody complex, and this antibody will be attracted to a eosinophil which is having Fc receptor, and once it is bounded like this, or a natural killer cell, they'll release the chemical, and those chemical will cause pores on the surface of the parasite. So this is another one. Next, neutralization. Here it is very clear. What they do is, they will bind all the epitope and mask all the epitope, so that antigen is no more it does not have any determinant to be exposed outside. So everything is been completely blocked. Likewise, it is being prevented by entering the membranes. And here, activation of complement system. As I said, the complement proteins will be activated because of the formation of antigen antibody complex. Once all the cascade once all the complement proteins are activated, the cascade system continues, and later on the end effect is that they release some kind of pharmacologically active chemicals that causes holes in the cell, and that causes lysis of the antigen. So these were the things what we